Namaste everyone. Welcome to the next lecture in current electricity. In this lecture, which will be a very short one, we will be only discussing about the limitations of Ohm's law in explaining the VI characteristics of various substances. Because though many substances are going to have a linear behavior of V versus I, but not that is only under certain conditions, because even when we are defining Ohm's law, we state that under constant conditions of temperature and pressure, V is directly proportional to I. So once we are going to post that condition, we are going to see in the upcoming slides that there are many substances which are not going to obey Ohm's law under their working conditions. And that is what we are going to state under limitations of Ohm's law. Now, based on whether they are going to behave as per Ohm's law or no, we are going to classify substances as ohmic conductors and non-ohmic conductors. Now, right on your slide here, you are seeing a linear behavior of V versus I for metallic copper and copper sulfate solution. So what happens over here? It's a direct variation of V versus I, right? So we call such conductors as ohmic conductors because they do obey Ohm's law, and the current does vary proportionally with increase in the potential difference of the potential difference applied across the ends of the material. So you can see here copper sulfate is an electrolytic solution over here that too obeys Ohm's law. And what happens when you're going to reverse the direction of the potential difference, reverse the direction of EMF? Now, when you are going to reverse the direction, the current also changes direction, but it still continues to vary linearly with the variation in potential difference. So such behavior is called ohmic behavior, or a perfect, in perfect accordance with the Ohm's law. But the same conductors will also show non-ohmic behavior if I am going to increase the amount of current that is going to flow through it. You can see here, this is again the characteristics of a metallic conductor. But do you see that as the current is increasing, it is showing non-ohmic characteristics? I hope you would have seen the previous lesson where we talked about the temperature coefficient of resistivity and the temperature dependence of resistivity. So what happens over here? As I am going to increase the current, the temperature of the conductor becomes hot, because we know by Joule's heating law, H is directly proportional to I square. The heat energy that is dissipated in a conductor is directly proportional to the square of the current. So what happens over here, as you increase the current, the heat energy dissipated in the conductor increases. As this increases, the temperature condition is going to change. And Ohm's law states that under constant temperature, the law is obeyed. But as temperature is going to increase, the non-linear behavior of the conductor comes into picture, as you see in this graph. So at higher temperatures, or when high current passes through the conductor, the same metallic conductor which obeyed Ohm's law starts to disobey it and begins non-ohmic behavior. So the first example for our non-ohmic conductor is what am I going to write over here? The first example is going to be conductors carrying high current. So this is what is going to be the first example of non-ohmic conductor. The same metallic conductor which we saw in the previous slide, this one. which is going to, sorry, I'm going to remove this. So this very same conductor, which is going to have an ohmic behavior, is going to have a non-ohmic behavior when high current is going to pass through it. So that becomes our first example. Let's move on to our second example, which is a water voltmeter. Hofmann's voltmeter is basically a device that is used in chemical laboratories to dissociate water into its components, that's hydrogen and oxygen. Now, if you look at the working of this water voltmeter, for the current does not begin to flow even after the application of a potential difference. That's because of the back EMF that's going to be developed due to the hydrogen and oxygen being liberated at the cathode and the anode respectively. Now, what is back EMF? You will be doing it in alternating current. That is an EMF. The word actually should give you a fair idea about it. The EMF which is going to be opposing the applied EMF. Now, what is EMF? For now, I will tell you EMF is the potential difference that a cell can offer, the maximum potential difference that a cell can offer. But we will be doing about EMF in detail in the upcoming lessons. So what happens, because hydrogen and oxygen are going to be liberated at the anode and the cathode, that's going to develop a potential difference that's going to oppose the applied potential difference. And as long as the applied potential difference is less than that back EMF, current will not begin to flow. This is something very similar to your frictional force, children. As long as you apply a force that's going to be less than frictional force, the object is not going to move. Isn't that clear, children? So think of it something like that. So your, our flow of current is very, very minimum. In some of your textbooks, you can see that water voltmeter graph will begin directly like this. That means the current is so meager that it's almost zero. If you take proper scales, that means it will always begin at zero. But if you are going to extend and expand your scale, you can still see a very meager amount of current. So this region becomes a non-ohmic behavior because your graph is not going to pass through origin. Your current is not zero when the potential is zero. Your current is zero even when the potential is not zero. And again, this becomes another example where Ohm's law is not obeyed, and another non-ohmic behavior in the VI characteristics, which is water voltmeter. Now this comes as a beautiful graph to us. This is about PN junction diode. Again, semiconductor. A p-type semiconductor and an n-type semiconductor is going to be fabricated to form a PN junction diode, about which you will be doing in detail in the chapter called semiconductors. Now what happens over here, you can see very, very clearly. I want you to observe this graph, pause, expand, zoom in your graph, and please watch the graph very carefully. This is the region where your voltage is positive, and this is the region where you apply reverse voltage. Is that clear? You can see over here, this is called as forward bias condition of the diode. That is the condition where it conducts electricity. Now, if you look at this, you see that for very small values of potential as low as 0.3 to 0.4, the current shoots up to 200 milliampere. Whereas look at the reverse region. For as high a voltage as 15 volt, your current still is in the range of microampere only. So that shows that, first of all, it is a non-ohmic behavior, and the behavior is different for different polarities of your potential difference. So another classic example of deviation from Ohm's law, another classic example of how this particular substance does not obey Ohm's law, even under normal temperature conditions, because here this is a completely different device. It's not a conductor, it's a semiconductor. And you see that for positive polarity of the potential, the behavior is completely different, and for negative polarity of the potential difference, the behavior is completely different. This barrier voltage is something similar to the barrier voltage that we saw in water voltmeter 2. So for till one particular, this is nothing but the energy gap, children. Please understand, if you had watched the previous video on temperature dependence on resistivity, we were talking about energy gap in semiconductors. Unless you cross the energy gap, unless the valence electrons move to the conduction band, you are not going to see current flow in semiconductors. So that is being emphasized in this graph also, barrier voltage. So unless this voltage is crossed, current doesn't begin to flow. And in the reverse direction, the more and more you try to make the material to conduct, the material breaks down. That's why we call it as breakdown voltage. Regarding all this, you're going to do in detail in the chapter called semiconductors. But for now, this is going to be our next example for a non-ohmic conductor. That's our PN junction diode. Now, this is a beautiful graph. This is the VI characteristics of a substance called a Thyristor. Now, a PN junction diode is two layers, a P-type and an N-type, while Thyristor is four alternate layers of P and N, PN, NP. So four alternate layers of P-type and N-type semiconductors that are going to be fabricated in order to form a substance. That is what we call as Thyristor. Now, right on face, you can see that this is definitely not obeying Ohm's law. And again, like a PN junction diode, the forward characteristics is different from the reverse characteristics. That is, for positive polarity of the potential, the characteristics is different, and the negative polarity, it is different. And look at the negative polarity is something similar to your PN junction diode. That is, the current doesn't flow for one particular voltage, and it suddenly increases at that breakdown point. And that is called avalanche region. Avalanche is a very simple English word where you say that some breakdown occurs at a very, very, very fast rate, right? The snow, when snow peaks are going to slide down, you call that as an avalanche. So there is an avalanche of charge carriers passing through the barriers, and we call that as the breakdown again. So that's your reverse region. But the beauty lies in the forward region, the forward bias region. Look at this particular graph, children. There are so many regions that we have to understand. You can see that for one particular voltage, you have two different currents. Don't you see that, children? For the same voltage, you have two different currents. Not only that, there is one particular region that is QP, or PQ, should I say, where you are actually reducing the potential difference while the current increases. Isn't that something new that we are looking at? You reduce the potential difference and the current increases. Is that clear, children? This is what we call as the negative resistance region, because the slope of your VI graph is negative. With decrease in potential, there is an increase in current. So that is a negative potential region. So we have 2-3 discrepancies over here. Number one, different behavior in the positive and the negative polarities. Number two, for different values, for same values of potential difference, you have different values of current. And then as you decrease the potential, the current still increases. Do you get that, children? So another classic example of deviation from Ohm's law. Another example for us for a non-ohmic conductor, which is a Thyristor, right? And then we move on to our final example for non-ohmic conductors, that is a gallium arsenide. This is again a semiconductor. You can see again here different behavior. You can see the region BC here, where AB is almost linear, BC becomes non-linear, and you see the region DE, which is again a negative resistance region, because the current decreases with increase in voltage. In the previous one, we saw current increases with decrease in voltage. Now here, current decreases with increase in voltage, again, negative resistance region. So if you look at this region, this is negative resistance region. If you look at this region, this is non-linear region. If you look at this region, this is a linear region. So again, we see that this substance does not obey Ohm's law. And another example for non-ohmic conductors. Please understand, these are not the only substances which do not obey Ohm's law. Again, if you had seen the previous video, we saw superconductors at different temperatures behaving with zero resistivity. We saw alloys which had a different behavior in the low temperature region and the high temperature region. Isn't it, children, where we saw that? And we also saw like this, as we are seeing here, that they do not have a linear variation of resistivity with temperature, which is why they do not obey Ohm's law too, because the resistance, according to Ohm's law, if I'm going to pick up resistance V by I, which is a constant, so this constant does not remain a constant when the temperature changes. So that is the reason for the condition on Ohm's law, that Ohm's law is applicable only under conditions of constant temperature and pressure. If not, there will be deviation from Ohm's law, which we saw with the help of various examples, beginning from the same conductors which obey Ohm's law to semiconductors which do not obey Ohm's law. So we come to the end of this simple lecture, and I hope you would have achieved these outcomes. You should have understood that though many substances obey Ohm's law, under certain conditions only, it's not a fundamental law, because there are many substances which do not obey the law and deviate from the law. And you should be by now at least a little bit clear in analyzing the characteristics, VI characteristics of various substances that conduct electricity under various conditions. So we are through with this part of the lesson. From our next class, we will be doing we will be studying about EMF and how are we going to look at batteries that are going to be cells that are going to be connected in series and in parallel, and we are going to look at some electrical devices like meter bridge and Wheatstone network. Till then, please do watch the videos carefully, repeat them if you want, keep studying and stay safe. Thank you.